Alright, today we're going to look at determining the differentiability of a function. Alright, we're going to look at determining the differentiability of a function. So right here we have f of x equals 2 over x minus 3. We want to determine if there's any places where this function is not differentiable. So let's talk about the word differentiable. What do you think the word differentiable means to me, or means to us? And I'm going to make you guys talk. I need to know what's coming to your mind when you hear that word. So just throw some stuff out.
It's different. Something. You can't differentiate.
So Charlie?
You can find where it's different.
Where it's what?
Different.
You can find where it's different. All right. Thank you for your effort. What else? Have we talked about the word? I don't know if we have. Have we talked about the word differentiation?
No.
That's the same thing as derivative. Find the derivative. Okay. So if we're connecting derivative to differentiation, then what can we connect to differentiable?
If you can find a derivative.
There we go. So it has to do with whether or not the derivative exists. Okay. If the derivative does not exist, then that means it's not differentiable. If the derivative exists, then that means it is differentiable. Okay. So what do you think we need to do in order to determine if something is differentiable? Find the derivative. Good, Emily. All right. What are we going to do to this thing to find the derivative? And why? Alexis?
It doesn't have a variable on the top, so I'm guessing we do chain rule.
We're going to do chain rule. What do I want to do before I do chain rule?
Move it to the top.
Very good. So we want to move this to the top. That's good. You guys are picking up some of the things I'm saying. All right, so if I do chain rule, -1 times 2 gives me -2. X minus 3 turns into a -2 exponent. And the derivative of x minus 3 is 1. So we end up with f prime of x equals -2 over x minus 3 squared. Now we're ready to determine whether or not there's places where we're not differentiable. Okay? Do you think there's a place where we're not differentiable on this problem? Now what did we just say differentiable means?
If there's a derivative.
If there's a derivative, okay? And we want to get specific if there's a derivative at each x value. So we're asking ourselves, are there any x values where I'm not going to have a derivative?
3.
In this case, 3. Why?
Because that would mean the bottom equals 0.
That makes the bottom equal 0, which means, yes, I've got an asymptote or something. I don't have a value there. So that means the derivative does not have a value at 3. If the derivative does not have a value at 3, then that means it's not differentiable. Okay? So what we're really asking is, well, let me see if you can connect some things for me. All right. What is it we're really asking about our derivative?
Does it exist in every x value?
Does it exist every x value? So what's something we've looked at that talks about existing at every x value?
Continuity.
There we go. Everybody hear Xavier? Say it again, Xavier.
Continuity.
Continuity. Okay? So when we're talking about differentiability of a function, we're really wanting to know, is my derivative continuous? Okay? If my derivative is continuous, then that means my function is differentiable. Okay? Now, let's make sure we're not getting things confused. What are we saying is differentiable? Which one of these two functions are we saying is differentiable? F of x or f prime? No. we're saying that f is differentiable, but we're looking at what to determine that? We're looking at the derivative to determine it. So we use the derivative to figure out whether or not it's yes or no, and when we figure out whether or not it's yes or no, we're talking about the original function. So we're using the derivative to figure something out about the original function. Everybody with me on that? Okay. Now, in this case, we should have known that it was not differentiable at 3 from the very start. Why do you think we should have known from the very start we weren't differentiable at 3?
It would already make it 0.
It's already 0 on the bottom, which means my original function is not continuous at 3. Okay? There's a requirement for being differentiable. What do you think that requirement is? Speak up. All right. Bigger picture. Bigger than the limit. Goes back to what Xavier was saying. I've got to be continuous. If I'm not continuous, then I can't be differentiable. Okay? And I already know by looking at this, I'm not continuous where? At 3. And if I'm not continuous at 3, then I'm definitely not going to be differentiable at 3. So I first have to be continuous in order to be differentiable. If I'm not continuous, then I can't be differentiable. Okay? In this case, what's my continuity issue? What? There's an asymptote here. Okay? So if I've got an asymptote, I'm definitely not differentiable. Alright, so let's look at the graph of this. So there's my graph. We said we've got an asymptote at 3. There's my asymptote at 3. Okay? Everywhere else is pretty good. Everywhere else is continuous. Everywhere else I'm going to be able to find a derivative. Okay? Alright, visually, what you're looking for is, obviously, number 1, we've got to be continuous. Number 2, is my curve smooth? So visually, is my curve smooth? If my curve is not smooth, then I'm not going to be differentiable wherever I'm not smooth. Okay? So my curve must be smooth in order to be differentiable. Now, what do I mean by smooth?
Like,
Right, all right. So, as Nancy said, an absolute value function. I'm going to do it in my pen. Anybody see it? There it is. All right, so as Nancy said, an absolute value function is going to look like that. Where am I not going to be smooth? I'm not going to be smooth right there. So that means I'm not going to be what there? I'm not going to be differentiable there. Okay, and we'll get more into that the more examples we do. Okay, but from our first example, the main thing I wanted you to know is, in order to be differentiable, I first must be continuous. That's what I wanted to know from our first example. Okay, if I'm not continuous, I'm definitely not differentiable. All right, next one. F of x equals x plus 4 to the 2/3 power. All right, so on the last one we had continuity issues. Are there any continuity issues with f on this problem? Tell me why. What are some things we need to look out for in order to have continuity issues?
0 on the bottom.
A 0 on the bottom. What? Piecewise.
What's it called? The absolute value.
Absolute value is technically going to be a piecewise function.
Okay.
But absolute value doesn't have any continuity issues. It's got differentiable issues, differentiability issues. Okay, so piecewise, what was the other thing we said? 0 on the bottom. There's one more thing I want to talk about. What's our other thing that causes continuity issues?
A hole.
Well, a hole's the 0 on the bottom. What? Trig is another one. There's one more that we're not getting yet. If I had the square root of x plus 5, what are my issues? What can I not have inside my square root? A negative. So the last thing is even radical. Okay, so for continuity issues, we're talking piecewise functions, we're talking what makes the bottom 0, we're talking what makes an even radical negative inside, and then as Tommy said, we're talking some of my trig functions have continuity issues. Okay? Of those 4, do I have any problems with those 4 with this one? There's no fraction, there's no trig, there's no piecewise. There is a radical, but what type of radical is it? It's an odd radical. Because if I were to change this, this is the same thing. That's the same thing as that. And what type of radical do I have?
Cube root.
I have a cube root. I have an odd radical. So therefore, no continuity issues. This thing is always continuous. So now we want to know, are there any differentiability issues? Okay, so what am I going to do to figure that out? Find the derivative. Find the derivative. So I bring the 2/3 down, x plus 4 stays the same. I subtract 1, that gives me negative 1/3. It doesn't matter in this case, but I'm going to go ahead and show that I took the derivative of the inside so that I know I did it. And then I need to rewrite this. What does it look like when I rewrite it?
2/3 times x plus 4 is 1/3.
2/3 times x plus 4 to the 1/3 power. Alright, so now that I have the derivative, what am I asking myself in order to figure out any differentiability issues? Are there any continuity issues with my derivative? So I'm asking myself those same 4 questions. Do I have any issues with those same 4 questions? You should be saying yes. Because what's going to make this right here can be 0, right? What's going to make it 0? A negative 4 is going to make it 0. Okay, so that means I'm not differentiable at negative 4. So when I pull up this graph here in a second, what's probably going to happen at x equals negative 4?
It's going to be an asymptote.
Now, I know there's not going to be an asymptote. Why do I know there's not going to be an asymptote?
Because there's no 0
There wasn't an asymptote in the original. Okay, so something else is going to happen. What else do you think is going to happen? Could be a hole. What's my other option? There's one more thing. What? I can't hear you. It's not smooth. Okay, very good. Not smooth. That's probably what's going to happen. So let me erase this and let's pull up the graph. And where should it not be smooth at? At negative 4. So there's my graph. What's going on at negative 4? It's not smooth. I am not smooth there. So therefore, I'm not differentiable there. I've got to be smooth.
So how do you know that it's not an asymptote?
Because it wasn't in the original. The original wasn't an asymptote. On the previous problem, I knew it was an asymptote. I knew there was an asymptote there because the original problem had an asymptote. If the original problem doesn't have an asymptote, I don't have an asymptote. Okay. So if there are no continuity issues with the original function, but there are continuity issues with the derivative, then we're going to be not smooth. Okay? And here's why I'm not differentiable. Tell me, what type of slope do I have over here on the left as I'm approaching negative 4? I have a negative slope. What type of slope do I have over here on the right as I'm approaching it? Positive. Okay? So with that jumps from a negative slope to a positive slope, and it jumps abruptly. That's when we have differentiability issues. When it's smooth like this, you know, my slope is gradually changing, okay? But here, it's sharp. It's a sharp change, and my slope does not gradually change. It jumps from negative to positive. On this one, it gradually changes and it's smooth. I'm differentiable. This one does not gradually change. It just abruptly jumps from a negative slope to the positive slope. That's when I have differentiability problems. All right, next one. Alright, square root of x minus 1. Square root of x minus 1. Alright, so what am I asking myself first? Are there any continuity issues? Are there continuity issues? Yes, where are they?
Even radical.
Yeah, I got an even radical. So specifically, what x values are giving me problems?
Negatives. 1.
Anything smaller than 1, correct? Anything smaller than 1. So I already know I'm not differentiable from -1 to 1 because the problem does not exist. So now I want to know, are there any other places where I have issues? So what am I going to do to figure that out? I'm going to take the derivative. All right, that's the same thing as x minus 1 to the 1/2. I bring the 1/2 down. New exponent is -1/2. Derivative of the inside is 1. And move the negative exponent. I get f prime of x equals 1 over 2 times the square root of x minus 1. Alright, so now what am I asking myself? Is that thing continuous? Is the derivative continuous? What are my continuity issues with the derivative? What? I don't want negatives inside an even radical. I've already taken care of that though, correct? I took care of that. Are there any other issues? Because there's one issue here that I didn't have in the original. What's the issue here? What's the continuity issue here that I didn't have in the original? Let's
0 on the bottom.
There we go. 0 on the bottom. I can get a 0 on the bottom here. I couldn't get a 0 on the bottom there. What's going to make me 0 on the bottom? 1. Okay? But I've already taken care of 1 because of that right there. So where is this thing differentiable?
Anything positive.
1 to infinity. So from 1 to infinity, this thing is going to be continuous, and I know the function is going to be what? Differentiable, which means it's going to look like it is smooth. That's what I want you to get. So I know from 1 to infinity, this thing is continuous, and it's smooth. So let's look at the graph to verify that. There's my graph. Notice 1 to infinity, I'm continuous, and the thing is smooth. Okay? So if it's differentiable, that means I'm continuous and my graph is smooth. All right, f of x equals x to the 1/3. All right. What do you got? Any continuity issues?
No.
Why not?
Radical.
Cube root, so I have no issues with the root.
Can't get a 0.
Can't get a 0 on the bottom.
Not piecewise.
Not piecewise. No trig. So therefore, that thing's continuous. Okay, that's what you should be going through in your head every time you're trying to figure out if something is continuous. Okay, so that means I'm ready to do what? Find the derivative. So I've got 1/3. I've got x to the negative 2/3. There's my derivative. So if I rewrite it, I have 1 over 3 times x to the 2/3 power. So now that I have my derivative, are there any issues with my derivative? Ariel, any issues with my derivative? What is it? You don't know?
asymptote. If x equals
All right, that's not the right wordage. The right wordage is I can get a 0 in the denominator, is what I want to hear. Okay, what's going to make my denominator 0? 0. Are there any other issues besides that? No. No trig, no piecewise. I've got a radical, but what type of radical is it? Odd. It's cube root. So my only issue is 0. So what does that tell me about 0? It is not smooth, yes. Okay, and then we're going to talk about a different word instead of pointy. Okay, here in just a second. Okay, so what do I know about my graph? Before I click over to it, what can you tell me about my graph?
At one point it's going negative, so
And
then
it's
the other
like
one is going
changes.
All right, so it's either going to go from positive to negative abruptly, or it's going to go from negative to positive abruptly. Everywhere else, what do I know about my graph? It's continuous and smooth. So everywhere on my graph is continuous and smooth, except for the x value of 0. And there, it's jerking from a negative to a positive slope or a positive to a negative slope. Okay? So there's my graph. But I've got something different in this one. I don't have what we just talked about. Okay? I've got something else. What's going on at 0? And think about a slope. Think about the slope. What's going on at 0? I have a vertical tangent line. Think back to your Algebra 1 days, because I know it's Algebra 1 because I was hanging out with the Algebra 1 teachers the other day, and we were talking about horizontal slopes and vertical slopes and being able to talk about the difference between the two. Okay? So if I have a vertical tangent line, or if I have a vertical line, what do I know about the slope of a vertical line? It doesn't exist. What's the word I want to use instead of doesn't exist? It's undefined. Okay? So undefined. So if I were to draw a tangent line right there, that's where I have differentiability issues. So we've got 3 visual cues on when I'm not differentiable. Obviously, we just talked about one. If I can draw a vertical tangent line, that means that I'm not differentiable there. What's the other one? An asymptote. So I'd rather talk about that more broadly. If I've got an asymptote, that means what? Right, but what else is going on in the big picture? What is it not?
Non-continuous.
It's not continuous, okay? So, vertical tangent line, I'm not continuous, or the other one we talked about was
It's not smooth.
it's not smooth, okay? Now, let's talk about that word I was wanting you to say about this right there. Vishali, what did you call it? Pointy, okay? The word we want to use is cusp. Okay? It has a cusp. So if we have a cusp, then that means we have a differentiability problem. Yes?
Could it also be called a vertex or vertex?
Yes, but we're going to call it a cusp.
sounds cool. Or on the cusp.
So visually, my visual differentiability issue problems are not continuous. So what does my function look like if it's not continuous? What are the possibilities? Gavin, what did you say? Asymptote is one option. What's another option? A hole. And the third option? A jump. Okay? So we're talking asymptote. We're talking hole. We're talking jump. So if I see any of those, I'm definitely not continuous, and which means I'm also not differentiable. Okay, what was my second visual cue? What did you say, Nancy? Vertical tangent line. Okay, and the last one? Last one is a cut. So if I just give you a graph and I say, is this thing differentiable or not, these are the things you're going to look for. Am I continuous? Is there a vertical tangent line? Do I have a cusp? If the answer is no to all those, that means I'm differentiable everywhere. If the answer is yes to one of these, then that means I'm not differentiable at wherever that's happening. With me?
What's a function that would look like it? Or like, what would a function look like if it was differentiable everywhere?
Parabola.
Oh,
I'm not sure I want to get into this one. You guys are going to hate this one. Well, no, we can do this.
yeah.
All right, last one. Last one, f of x equals the absolute value of x minus 1. F of x equals the absolute value of x minus 1. Alright, so if I'm going to determine if it's differentiable, what do I want to think about first? Continuity issues. And since it's an absolute value problem, are there any continuity issues? No. Okay. No zero on the bottom. Technically it is a piecewise function, but we know it's a continuous piecewise function. No radicals and no tangent problems. So this thing is continuous. Okay? And this one we're not even going to take the derivative because we know what this thing looks like. What do we know this thing has in it? We know it has a cusp. Okay? So all we have to do is figure out what? Where. So we know this thing has a cusp. We just have to figure out where it is. Does anybody know how to figure out where it is if you're dealing with an absolute value problem? Set what equal to 0?
The absolute value.
Set what's inside the absolute value equal to 0. Okay, if there was something else like plus 3 was a part of that, I don't care about the plus 3. All I care about is what's inside my absolute value. So set that equal to 0 and solve. And I get x equals 1. So what do I know is happening at x equals 1? I have a cusp, which means I'm not what? I'm not differentiable at that spot. Okay, so if I graph it, there it is. Notice my cusp is right here. Not differentiable. Okay. Now, you're going to have to justify, if I give you a graph and you tell me it's not differentiable, you're going to have to tell me why. Okay? There are 3 reasons why I'm not differentiable. Okay? That right there is reason number 1. Okay? Reason number 1 is it's not continuous. Okay? Reason number 2, you're not going to be able to tell me because there's a vertical tangent line. You have to tell me what a vertical tangent line tells me about the derivative. If I have a vertical tangent line, what does that tell me about the derivative? There's no slope at that point, so what's the word I want to use instead of no slope? Undefined. So what I want to say is derivative is undefined. Okay, so if I have a vertical tangent line, that means the derivative is undefined. Okay, and if there's a cusp, we haven't talked about this yet. That's an F. Okay, so when I write that down, what am I saying? What? Right, but what's a easier way to say what all this is meaning?
The limit as it approaches from the right is not equal to the limit as it approaches from the left.
And the limit of what?
As it
Right,
approaches.
and what are we going to call that besides f prime of x if I want to generalize it? The derivative. So I'm going to say the limit of the derivative does not exist at whatever my x value is. Okay? So the limit of my derivative does not exist at whatever x value. I thought we had some graphs to determine differentiability.
It's a good one. Strong.
He's like
Very ugly people.
he has to oftentimes he has to move like
I figured he was rolling.
he can do that. But it's just it makes it easy.
Oh, does he roll like a cone does? Like this point won't move because there's not as much surface area, and this one's just like.
It's like this.
Especially since none are like springs.
That's so sad.
So you
Yeah, because this point is like it's going like this.
so he's like really thick like
Alright.
yeah.
No, we'll stop there. Let me draw a couple things up here just to make sure we've got what we need. Alright, so let's draw some of the things you might encounter.
Oh, that's a closer.
Alright, so you might get a function that looks like this, and they might say, alright, is there a place where I'm not differentiable? In this case, where am I not differentiable?
At the cusp.
Whatever that value is right there, let's call it 2. So I'm not differentiable. Okay, what's my reasoning going to be?
The limit of the derivative
The limit of the derivative
does not.
does not exist at x equals 2. Okay, so if I give you a graph and I ask you to tell me where it's not differentiable and why, you're going to say not differentiable at 2 because the limit of the derivative does not exist at 2. Okay, that's what I'm going to want. Okay, what about that one? Derivative is undefined. So I'm going to say not differentiable. Let's call this one 1. Not differentiable at x equals 1 because the derivative is undefined at that x value, at x equals 1. Okay? Okay, so let's call that -2 right there. Okay, you're going to tell me not differentiable at negative x equals -2 because f is not continuous at x equals -2. Okay. Make sure you understand that when I ask for explanations, these are the explanations I want. Yeah, not continuous. And those are the explanations I want. On our last test, we were talking about something not being continuous, and then I asked for an explanation. You weren't giving me the explanations I wanted. You were just trying to come up with something on your own. Anybody remember the 3 reasons why I'm not continuous? What are the 3 things that could be a continuity problem? Yeah, those aren't it. What are the 3 things that have to happen in order to be continuous? I have to have a limit. I have to have a function value, and that has to be the same. So if you're going to tell me I'm not continuous, then you got to tell me one of those 3 things is not happening. I don't have a limit. I don't have a function value. The limit and the function value don't equal. So if you're going to tell me I'm not continuous, that's what you've got to tell me. If you're going to tell me I'm not differentiable, then you got to tell me I'm not continuous, the derivative is undefined, or the limit of the derivative does not exist. Okay? So if I ask for where am I not differentiable and why, those are the whys. If you give me a y other than one of those 3 things, automatically wrong. Okay? On the last one, I some of you had located the correct spots and were saying some good things, but you weren't telling me what I wanted. And that's why I circled it and I said I need a better explanation. That's what I meant. I mean, there are exact explanations. There are exact explanations. Okay? And that's a lot. You got to explain a lot of things when you're taking the AP test, and I'm going to give you exact things to say. So when I tell you it needs to be exactly that, that's what it needs to be. Got it? So if I'm not differentiable, you got to tell me I'm not continuous, derivative is undefined, or the limit of the derivative doesn't exist. Got it? Okay. We'll add a little bit to that on Monday and do some work on it on Monday. You've got a weekend with no calc work. No calc practice. Yeah. So you're wanting to graph it and determine it that way?